Hi, so in this video we'll be going over VSEPR theory and a little extension on polarity. I'll be doing that simultaneously just so that we can get that both the lectures covered. But VSEPR theory, what is VSEPR theory? VSEPR theory basically gives us a rule on how to deal with, whoops, I went back too much. Let's see. There we are, somewhere over here. Yes. So we'll be needing, so I'll basically print these two pages out from my PDF and I will give it to you on a test, page 182 and 183 from your textbook. You'll be needing this while practicing as well because you will be given this on a test. The VSEPR theory basically tells us when we're drawing Lewis diagrams what VSEPR theory is. So what does VSEPR stand for? Valence shell electron pair repulsion theory. So what it says is, for example, when we draw water, we might draw, the structure of water, the Lewis diagram might look something like this. But VSEPR theory basically gives us an idea of the shape of water. Not the movie, the actual shape of a water molecule. Here, the valence shell, this is basically the valence, electron pair. So electron pair could be a lone pair or it could be an electron pair in a bond. So repulsion. So what it says is these electron pairs will repel each other and the atom will orient itself in a way to minimize that repulsion. So what water will actually look like is it will look like this. So it'll look like that. And again, do we really have to, I will tell you that the lone pair, the repulsion here is the greatest compared to the lone pair, bond pair repulsion compared to the bond pair. So a more accurate diagram would generally be, if we were to try and draw this somewhat to scale, it might look like this. With the greatest repulsion here, there's significant repulsion here, the least repulsion between two bonding pairs. Right? But do you need to really know all that? No, not necessarily. You just have to know that according to this repulsion, the molecule is going to align itself in a certain shape, and this shape is given conveniently in this table. So there's could be linear, trigonal, planar, angular, tetrahedral, trigonal, pyramidal, all these different kinds of shapes depending on how many lone pairs and how many bond pairs there are. Again, bond pair, I mean the pair of electrons in a bond. That's what I mean by bonding pair. So depending on how many there are, you say that it has a certain shape. Now, VSEPR notation involves the use of three letters, A, X, and E. A is the central atom. There's always one A. Without fail, there's just A1. It's just A. And then X is the number of bond pairs, so basically the number of bonds. So if for water, for example, we know that water has two bonds, so that would be an AX2. And then E corresponds to the number of lone pairs around the central atom. Again, I'm not bothered about how many lone pairs there are around surrounding atoms. Just the central atom is what I'm focusing on. So in water, for example, there will be two lone pairs along the central atom. So use write VSEPR notation for water as AX2E2. And once you know that, you go to this table, you go down to AX2E2, you find that, and you say, okay, it's an angular orientation. And then you draw water in this shape, which is basically the shape that you draw water, the correct shape that you draw water. So you can't draw water like this anymore. This is wrong. This is a good starting point to get to this structure, basically, because you see, okay, I have two bonds and two lone pairs, so I know it's AX2E2. Therefore, the actual water molecule looks like this. And that's how you find the structure of water. I will point out that in terms of polarity, this bond will be polar because the oxygen-hydrogen bond has a dipole moment associated with it. It's a polar, both of those are polar bonds, and they do not cancel each other out. They're not pointing in opposite directions, and therefore they do not cancel out. The lone pairs you can consider to have no polarity. You can consider to have extreme polarity. It really doesn't matter. They don't cancel out with the bond pairs, and therefore this is a polar. Water is a polar molecule. We already know this. There will be very few cases where the molecule is non-polar, and we'll talk about those cases as they come up. So, this is just okay. So these are perhaps examples of the non-polar type with 0 lone pairs. So if we jump ahead to our presentation here, we'll see if the molecule has a lone pair, it is polar. If the molecule has a net charge, it is automatically polar to the extent of being an ionic. And this is, for example, like if we take our NO3 minus or our PO4 3 minus, these are, even if they do cancel out, they are automatically polar because they have a net ionic charge. So they're the molecule as a whole has a charge of 3 minus, which makes it incredibly polar. So much so that it forms ionic bonds, not only dipole-dipole bonds. So that's pretty polar right there. And if a molecule has no lone pair, so the basic VSEPR shapes, we'll talk about that. There are two possibilities. Either substituents are all the same. Substituents are the atoms that are added to the central atom. So these are the things that are sticking out of the central atom. Sorry, one moment. Sorry. Yeah, substituents are the things that are hanging off. So the substituents in water would be the hydrogens, or the substituents in CF4 would be the 4 fluorines. Anything that's not the central atom is a substituent. Substituents are the things that are sticking out of the central atom, so to speak, or sticking out of the main body of the molecule. If the substituents are different, then it's polar. So we'll go over some examples and we'll see what we mean by this. So if we go back to our VSEPR shapes, was it this one? Yes, it was this one. So, okay, we'll do, in class we went through it in a different way. We'll do these first because this is how I prefer to learn it. Again, it's really up to you. So here we have a case of 0 lone pairs. So here are basically our basic VSEPR shapes. So this is our basic organization of the molecule. So BeF2, that's BeF2. This is the structure. If we draw the Lewis theory, there's no lone pairs on beryllium. There's not enough electrons. There's like 6 lone pairs on fluorine. And beryllium is fine with 4, so this is the complete Lewis structure. We'll see here that there's 2 bonds, and to maximize, again, around the central atom, this is an AX2 shape because there's 2 bonds and 0 lone pairs, and this will be an angle of 180 degrees, so it'll be linear as a shape. Or AX2, if you go back to here and check, you know, AX2 is linear right there. BF3 looks like this. Again, a bunch of lone pairs around the fluorines, but no lone pairs around the boron. This will be an AX3 because, again, 3 bonds near 0 lone pairs around the central atom. This is what we call trigonal planar because it forms a triangle, sort of, and it's on the same plane, so there's no 3D element yet. This will, and as you might expect, these two, or actually all these cases, are non-polar. Why? Because there's a dipole moment here pulling electrons this way. There's a dipole moment here pulling electrons this way. These two will cancel out. So the molecule as a whole will be non-polar. Same way, this too, if you've learned in physics about vector addition, you can apply the same principle here. If you add these 3 vectors using proper vector addition, they will all cancel out. Or you can imagine that these two are canceling out the left and right, but they're still pulling up, which is canceled by this pulling down. And so basically the dipoles will all cancel out. This is also a non-polar molecule. Let's do CF4. CF4 has a tetrahedral structure, which means it's 3D, which is indicated by the dashed and the wedged lines, which indicates that this is coming out of the page and that's going behind the page, so to speak. In terms of here, again, the base is a triangle and here's a pyramid, but this is called which is a tetrahedron. This is a tetrahedral structure of AX4. Again, this will be non-polar because these three will have a net pointing straight down, which is cancelled by the net pointing straight up of the fluorine, and therefore you have a net zero dipole non-polar molecule. So this is a tetrahedral shape. We can do SbCl5 and SF6 separately. SbCl5. The structure basically looks like this, where you have three these are called the equatorial bonds because they're lying on a flat plane, and we have axial bonds that are sticking up vertically out of the plane. So these are called axial bonds. No, I'm pretty sure it's not axial, it's axial. And equatorial bonds or equatorial plane is over here, right? And therefore this will be a trigonal because it's a triangle, bipyramidal because you have a pyramid on top and you have a pyramid on bottom. So that's a trigonal bipyramidal structure for an AX5 molecule. This will again be, you might guess, non-polar because you cancel out, all these things cancel out basically. Up cancels down, this cancels this. Same way for the SF6 is a octahedral structure of AX6. So this is sulfur. You have, instead of a triangle, you basically have a square, then you have an up, and you have a down. I'm not putting the lone pairs because that takes too much time, but you have to do so on a test, blah, blah, blah. Again, square in the plane, and then one pointing up and one pointing down on the plane of the square. So this is an octahedral array of 6. This is also non-polar because they all cancel out. So again, these are the basic VSEPR shapes. These are the shapes that I did say would be non-polar. But again, you can easily make it polar just by changing, for example, instead of CF4, if it was CHF3, now you have a kind of distortion where you have 3F, but one of these is a hydrogen. So the dipoles don't cancel out anymore. So as soon as you have this kind, even though it is still a tetrahedral, there's no change in the shape, it's still an AX4, but it is now polar because you have different substituents and not all the same. It's not F4, it's H and then 3 fluorine. So they don't cancel out here. There will be a net dipole pointing in some direction. And that makes it a non-polar molecule. Again, there are a couple of cases. We'll run over these really quickly. If you have a trigonal planar, so an AX3, and you replace one of these bonds with a lone pair. For example, SnCl2 looks like SnClCl. Here you have, instead of your trigonal planar, before you could have an SnCl3 here. Now we've removed that and replaced that bond with the lone pair. Because the lone pair repulsion is greater, it kind of pushes down on this more, so this angle, these two chlorines will get closer together. But again, you just realistically, as soon as you draw the Lewis structure, you figure out AX2E, and you say, okay, I know this is going to be a bent or angular by looking at my chart here. AX2E is angular. And that's basically all you have to do. Tetrahedral, there could be AX3E or AX2E2. This is water, for an example. We saw the bent or angular structure. AX3E corresponds to a trigonal, trigonal pyramidal. It looks like this. Basically, in the tetrahedral, one of these bonds is replaced with a lone pair, which you have a triangle and you have a pyramid from the central atom. So that's, for example, PCl3. We went over water, or H2S, for the bent or angular structures. This is probably the most complicated one. The trigonal bipyramidal has the most variations. You could have an AX4E, which would make it T-shaped, for example, TE. see if I can. Nope. I do not know why this suddenly stopped working. But, oh, this stopped working too. Oh, my app's not working. Okay, give me a second. Alright, to continue, we have TCCO4, TE, and then, again, we started off with, for example, an axial structure, but instead, we have now removed one of the things from here and added a lone pair, so this kind of pushed down a little bit, but you can see here that it basically looks like a seesaw if you like look at it sideways, like if you think this would work. Oh, never mind. Oh yeah, I can do that. Can I rotate? Done. No, that did nothing. And never mind. I have to figure out how to rotate using my stylus, but that's for another day. If you rotate it this way, okay, but I mean, it doesn't matter if you see a seesaw or not. No, it's just called a seesaw. You just look at this chart and you say, okay, this is a seesaw shape, and that's all you need to get from that. Again, the BRF3, if you remove one more of these bonds, you get a T shape. It looks like a T basically. You have this So both of these have been replaced essentially with lone pairs, and the bond is over here. So you have basically a T, which is again AX2E3, AX3E2, and the linear is AX2E3, where you have 3 lone pairs, 2 bonds. Again, it looks linear basically. XEF2 is an example of that. So those are the extensions of trigonal bipyramidal. Octahedral, you have a square pyramidal and the square planar, corresponding to AX5E and AX4E2 respectively. Hopefully I don't have to draw those out. They're basically some of these, and if we see them in the practice, we'll of course do them in the textbook work, so we'll do them. So that's it for these guys. So I will sign off, and then we'll see everybody in class.